All right, so this is a lesson to go with activity 4, which is modeling polynomial functions in real life situations. The first example we're going to look at has one to do with building some sort of enclosure or fencing and using materials. So here it says there are 40 meters of fencing to enclose a rectangular pen. So I have a diagram drawn right here. The dimensions that we have in a rectangle are length and width. And when we think of that 40 meters of fencing, it's talking about the perimeter. So we know that the perimeter formula is 2L plus 2W. So in this particular case, I know that I have 40 meters that need to be spread evenly to the length and the width. So I'm going to isolate for W. So what that means is I'm going to rearrange so that I have W in terms of L. If I divide both sides by 2, I'm left with this expression. So now when I label my dimensions on my graph, I know that my width will be W and my length will be 20 minus L, which I need to actually adjust this because now I still have two different variables. So instead of doing it this way, I'm going to have L and 20 minus L. The area can be represented as L times 20 minus L. And if I were to expand that, that's going to be 20L minus L squared. You're being asked to graph the function. So when I do that, this is the picture that I get. We see we have a parabola that's opening downwards, and it's asking to find the maximum area. So the maximum is going to happen at the peak. So the coordinate of this point is 10 and 100. So that means that the area is going to equal 100 meters squared, and I know it's meters squared based on the units that we started with. Then it asks for the dimensions that give the maximum area. So this 100 meters squared occurs when L is equal to 10. So the L is kind of like the X. So therefore, W is the same as 20 minus L, which is 20 minus 10, which equals 10. So our dimensions are going to be 10 meters by 10 meters, which if we were to multiply those two numbers together, we end up with an area of 100. And if we were to add them in terms of perimeter, we would end up with 40. So we've satisfied the conditions. The next example, we're starting off with a ball being thrown from a balcony. And it's modeled by negative 4.9 t squared plus 10t plus 35. Here's the graph of the function. So we see once again it's a parabola that's opening downwards, which tells us we're going to have a maximum value. And on this graph right here, it looks like it's at about 1 and it's pretty close to 40, maybe a little bit less. Determine the maximum height of the ball above the ground. So the maximum height, based from our graph, will be at 40 meters. How long does it take the ball to reach the maximum height? So the time where that occurs is about 1 second. And then it's asking us for the domain and range of this function. So the domain is going to be x is an element of the reals, such that. Domain in this case is really important. We need to talk about context. So the ball can only start at 0. Negative time doesn't make sense. So we're dealing with this a little bit right here. And we're only going to go as far as, I just need to adjust this because it's not x as my variable, it's t because it's time. And then we're less than or equal to, the ball hits the ground, it looks like around 3.9. So I'm just estimating here from our graph. The range is going to be h is an element of the real. Since that's our y-axis, it's represented by height. We are going to have a minimum value of 0 all the way up to about 40. So when we're looking at domain and range, Yes, you have to consider the graph as a whole, but when you have a particular situation, you need to define it specific to that situation. Negative time values don't make sense. Once the ball hits the ground at this value right here, that's as far as it can go. So we want to denote that when we're writing our domain. The third example we have is going to involve a cubic. So a piece of cardboard 6 centimeters long and 4 centimeters wide is used to make a box. So I'm going to start off by sketching a rectangle. Okay, so I have a rectangle here. In order to take a rectangle and turn it into a box, you're going to cut a square out of each corner that is the exact same size. So these would each be x in terms of dimensions. So now when I label, this is 6 as the whole length minus 2x. And then on the side here, we're going to have 4 minus 2x, because you're cutting the x out of both sides, so we need to include it twice. If I show this as a 3D shape, which is what we're doing to make the box, we know that the height will be x. We'll have 6 minus 2x, and then 4 minus 2x. Those are our dimensions. In letter B, you're asked to write the volume in terms of x. So that's what this expression is right here. The next line, all I've done is I've expanded the function, so I have 4x cubed minus 20x squared plus 24x. So when you're expanding polynomials, you're using FOIL, you're making sure that you're multiplying your x's together and then combining like terms. From here, I am now going to graph the function. Okay, so this is the function. I'm going to change the domain and range. Okay, so the x is fine, but the y we're going to change so that we go from negative 10 to positive 10 with an increment of 1. Okay, so that's the graph that we end up with when I alter. So we see it's a cubic, so it makes sense that I have 2 turning points, either minimum or maximum values. So in this case, it's asking the maximum volume and the dimensions that give this volume. Now let's talk a little bit about what makes sense in this case. If we look at the equations that we have up there, x has to be between 0 and 2. So x has to be between here and here. And the reason why it needs to be between 0 and 2 is because any other value, if you substitute it into 4 minus 2x, you're going to get 0 or a negative number. And that doesn't make sense. So we'll have negative 2x equals negative 4. So x is equal to 2. So for your domain, x is an element of the reals such that 0 is less than x, which is less than 2. So it kind of eliminates what we need to consider for the rest of the graph, because really it's only this part right here that I'm going to be worried about. It then asks us to find the maximum volume. So I'm going to read this value. So the volume at a maximum, I'm actually going to remove that blue for the moment. So the volume looks like it's at about, this would be 9. So it looks like it's at about 8.5 centimeters cubed. It occurs when x is equal to, it looks like it's about 0.9 centimeters. So it's asking for the dimensions. We have 3 dimensions. So therefore, x is equal to 0.9 centimeters. 6 minus 2x is going to equal 6 minus 2 times 0.9, which is going to be 6 minus 1.8, which is going to equal 4.2 centimeters. And then finally, we're going to have 4 minus 2x, which is going to equal 4 minus 2 times 0.9, which equals 4 minus 1.8, which is going to be 2.2 centimeters. So the piece of cardboard that's going to be folded is going to have dimensions of 0.9 centimeters by 2.2 centimeters by 4.2 centimeters. So in this section, once you've generated your equation for a lot of these questions, you're going to be getting your answers from reading the graph. So obviously there will be a little bit of leeway in your answers. If you had said that it was 0.91 or 0.8 or something along those lines, as long as the rest of your work is appropriate, you will still get full marks because there is some level of estimation involved in here. Hopefully this will help you complete the activity in 4 where you have to submit the responses to 3 different questions. Good luck, and if you have any questions, please send me an email.